Ancient astronomers mapped the cosmos with only their eyes and intellect. Their ability to predict cosmic cycles with astonishing precision remains one of history's most compelling puzzles. By the end of this story, you will understand the sophisticated methods these early sky watchers used to unlock the universe's deepest rhythms. We will reveal how they tracked planetary movements across generations and built mathematical models without computers. What timeless human quality do you think made their incredible discoveries possible? They began with the most fundamental tool of all, patient observation. Night after night, year after year, ancient sky watchers across different continents documented what they saw. In Mesopotamia, Babylonian scribes pressed intricate markings into soft clay tablets, logging the precise movements of planets and the recurring dates of lunar eclipses. Far across the world, Mayan astronomers carved complex calculations into stone, tracking the cyclical dance of Venus with an accuracy that still feels staggering. These were not casual glances upward. This was a disciplined, multi-generational project. A single observer's lifetime was too short to see the full patterns, so knowledge was carefully passed down, each generation adding its own meticulous records to a growing celestial library. From this vast collection of data, repeating cycles began to stand out from the background noise of the heavens. The cosmos, which seemed so chaotic, started to reveal its deep, rhythmic order. What drove this immense collective effort? It was a combination of sheer practical necessity and profound wonder, knowing when to plant crops when rivers might flood, or when to hold sacred ceremonies depended on reading the sky's clock. But beyond survival, there was a deep human yearning to comprehend our place in the universe. This foundational work, this slow and steady accumulation of knowledge, provided the first reliable keys to predicting the future itself. Their first great tool required no advanced mathematics, only an unwavering commitment to watching the sky. Picture the steady hand of a Babylonian scribe, carefully pressing a stylus into a damp clay tablet by flickering lamplight. Night after night, he marked the moon's position relative to a specific star, creating a permanent log of its journey. This was not a hobby, it was a sacred scientific duty. The true breakthrough came not from watching for a year or even a single lifetime, but from the patient accumulation of records across generations. When one astronomer passed, his successor inherited his life's work, adding his own observations to a growing celestial archive that stretched back for centuries. From this monumental collection of data, patterns began to emerge from what once seemed like random celestial motion. They noticed, for instance, that a similar pattern of eclipses repeated itself every 18 years and 11 days, a cycle we now call the Saros cycle. This was the moment raw data transformed into a predictive tool. By looking backward through centuries of meticulous logs, they could suddenly see forward, forecasting the future dance of the sun and moon with stunning reliability. Their patience granted them a form of time travel, allowing them to peer into cycles far longer than a human life. But identifying a pattern was only the beginning. The true intellectual revolution occurred when these sky watchers began to translate the rhythms of the cosmos into the universal language of mathematics. They moved beyond simply recording what they saw to building abstract models that could simulate the heavens themselves. In ancient Greece, philosophers and mathematicians devised intricate geometric systems to represent the perplexing loops of the planets. Instead of accepting the erratic motion at face value, they imagined a celestial machinery of perfect circles and spinning spheres, a cosmic clockwork whose mathematics could predict a planet's position years in advance. Meanwhile, on the Indian subcontinent, scholars were mastering a different mathematical toolkit. They employed incredibly sophisticated trigonometric calculations, working out the sine and cosine functions to track the moon's subtle wobbles and the sun's changing speed with breathtaking precision. This was not just description, it was prediction. Their models allowed them to run the cosmic clock forward, calculating the future positions of the moon, sun, and planets with an accuracy that would not be surpassed for over 1,000 years. Consider the sheer mental leap this required. With no computers and only the most basic tools, these thinkers grasped profound concepts like proportionality, the idea that one set of numbers could perfectly mirror the behavior of the heavens, and periodicity, the understanding that cosmic events are bound by repeating cycles. This was the monumental shift from merely seeing the patterns to truly understanding the underlying rules. It was the moment humanity learned to foresee celestial events not through intuition, but through calculation. Yet the most brilliant mathematical models needed to be tested against the real sky. This demand for tangible measurement led to the creation of beautifully simple yet profoundly effective instruments. A stick planted upright in the ground, known as a gnomon, became one of humanity's first scientific tools. By patiently tracking the length and direction of its shadow throughout the year, an observer could pinpoint the exact days of the solstices and equinoxes, marking the sun's highest and lowest points in the sky. This was more than just telling time, it was grounding the vast cosmic cycle in a single, observable line of shadow on the Earth. From this basic principle, toolmakers and thinkers engineered increasingly sophisticated devices. The armillary sphere, a skeletal model of the celestial sphere with rings representing key circles like the equator and the ecliptic, allowed astronomers to visualize and measure celestial coordinates. The astrolabe, a handheld marvel of engraved metal plates and rotating pointers, became a portable computer for the stars, capable of telling time, calculating altitudes, and predicting risings and settings. These were not complex machines with moving parts, but elegant solutions that translated the geometry of the heavens into something that could be held in your hands. Their true power, however, was unlocked when paired with another monumental human invention, the calendar. Civilizations did not merely create lists of days, they engineered entire temporal frameworks synchronized with the cosmos. The Maya developed the long count, a linear calendar that measured vast stretches of time, allowing them to place historical and future events within a grand cosmic chronology. In China, scholars perfected a lunisolar calendar, a delicate dance that reconciled the cycles of the moon with the longer solar year, inserting extra months when necessary to keep the seasons in their proper place. This synergy between simple instrument and sophisticated timekeeping was the final piece of the puzzle. By aligning their man-made calendars with the unwavering rhythms of the sun, moon, and planets, they constructed a reliable cosmic clock. This allowed a priest in Central America to know the precise day Venus would appear as the morning star, or a court astronomer in China to announce the exact moment of the winter solstice for the emperor's ceremony. Their astonishing precision did not come from overwhelming technology, but from the clever application of fundamental principles. It was a powerful demonstration that to measure the universe, you first needed to understand the elegant simplicity of its rules. The stars were not merely points of light, they were the living script of the gods. This profound belief transformed the night sky into a sacred text to be decoded. For the ancient Egyptians, the heliacal rising of Sirius, the star they called Sopdet, was not just a seasonal marker, it was a divine herald, its first appearance at dawn signaling the imminent, life-giving flood of the Nile. Their entire agricultural cycle and the festivals that sustained their society were orchestrated by this celestial event. They built their temples with precise alignments so that on certain days of the year, the sun would shine directly down the central corridor to illuminate the statue of a god within. This was architecture as divine communication, a permanent bond between earth and heaven. In Mesopotamia, Babylonian priests were the ultimate celestial interpreters. They believed the gods communicated their will and warnings through omens in the sky. A lunar eclipse might foretell the death of a king. The appearance of a comet could signal war or famine. The pressure to correctly read these divine messages created an unparalleled incentive for precision. Their astronomical diaries, which logged everything from planetary positions to weather, were essentially databases for divination. A mistake in prediction was not just a scientific error, it was a failure to understand the gods themselves, a misstep that could jeopardize the entire kingdom. This spiritual imperative demanded and rewarded extreme accuracy. It drove them to discover the long-term patterns that governed eclipses and planetary motions, not out of abstract curiosity, but to anticipate the mood of the deities. This fusion of faith and observation had a powerful consequence. It embedded astronomy into the heart of cultural life. The knowledge was not kept in an isolated laboratory. It was essential for royal ceremonies, for setting the dates of religious festivals, and for legitimizing the rule of kings who claimed a direct connection to the cosmos. The priest who could predict an eclipse held immense power, but he also bore a sacred responsibility. This cultural framework ensured that the craft of observing the sky was preserved, funded, and passed down through generations of scribes and scholars. Their quest to predict the cosmic cycles was at its core a quest for order. They sought to align human society with the perceived harmony of the heavens, to live in a world where the rhythms of the earth mirrored the rhythms of the sky, creating a stable bridge between the human and the divine. The Babylonians left us with proof of their cosmic foresight, etched deep into clay. Among the thousands of tablets recovered, the most remarkable are the astronomical diaries and procedure texts that detail their methods for predicting eclipses. These were not vague prophecies but calculated forecasts. Their key was the Saros cycle, a rhythmic pattern they discovered in the heavens. They understood that after a period of approximately 18 years and 11 days, the sun, earth, and moon returned to nearly the same relative positions, and a similar eclipse would occur. To grasp the scale of this discovery, consider the dedication it required. An astronomer would begin his observations as a young man. He would note an eclipse, and then he would spend his entire career watching the sky, patiently adding to the records of his predecessors. He would grow old, and the crucial pattern would only reveal itself as his own records were combined with those of his successors. This was a science that truly unfolded across generations. Their mathematical approach was both elegant and powerful. They used a system of arithmetic progressions, adding fixed amounts to the timing and position of each eclipse in a long series. This allowed them to build a predictive model that could run forward in time, projecting the dates of future events with startling reliability. The sophistication of their technique rivals modern computational thinking, yet it was achieved with nothing more than a deep understanding of numerical patterns and an unwavering faith in celestial order. Their legacy is a profound reminder that the universe's deepest secrets are not always hidden in complexity. Sometimes they are waiting in plain sight, revealed only to those who watch with patience and record with care century after century. Deep in the humid Mesoamerican jungle, Mayan astronomers gazed at the brilliant point of light we call Venus. They saw something far more significant, a celestial deity whose movements dictated the rhythm of life itself. Their calculation of its cycle stands as one of the ancient world's most stunning intellectual achievements. They determined that Venus took 584 days to complete its synodic period. the time it takes to go from being the morning star to the evening star and back again. Modern science calculates this period as 583.92 days. The Mayan figure is off by less than 2 hours per cycle, an almost unimaginable accuracy achieved through generations of naked eye observation. This was not abstract math for its own sake. It was woven into the very fabric of their world. The Dresden Codex, one of the few surviving Mayan books, contains detailed Venus tables that project its movements forward for centuries. These charts were essential because Venus was intimately linked with conflict and power. The first appearance of Venus as the morning star after a period of invisibility was considered an inauspicious time, a moment when the gods' influence could bring chaos. Military campaigns and ritual warfare were often scheduled around these celestial events, an attempt to harness the perceived power of the heavens for earthly purposes. But the influence extended beyond the battlefield. The Venus cycle was synchronized with their sacred calendar, a 260-day count known as the Tzolk'in. Every 61 Venus years, a period of just over 100 solar years, the entire cycle would realign perfectly. This grand convergence of cosmic calendars was a moment of profound ceremonial importance, a time to reaffirm the covenant between the people and the gods. How did they achieve such precision without telescopes or clocks? It was the result of a sustained, society-wide project. Priests and scribes dedicated their lives to watching the horizon, noting the exact day Venus would disappear and then reappear. This data was compiled and refined over centuries, allowing them to smooth out tiny observational errors and distill the planet's true rhythm. Their work demonstrates that cultural necessity can be the most powerful engine of discovery, driving a civilization to map the heavens with a clarity that would not be surpassed for 1,000 years. While the Maya tracked Venus with breathtaking precision, a different intellectual revolution was unfolding across the globe. In the bustling centers of ancient Greece, thinkers were constructing a new vision of the cosmos, one built not on cycles alone but on geometry. They asked a daring question: what if the universe operated according to elegant, mathematical rules that the human mind could uncover? Hipparchus, one of the greatest of these astronomers, made a discovery that reshaped their understanding of time itself. By comparing his own star charts with those made by his predecessors, he noticed something peculiar. The position of the stars was slowly drifting over the centuries. He had discovered the precession of the equinoxes, a slow wobble in Earth's axis that completes one cycle every 26,000 years. To detect such a subtle motion without a telescope was an act of genius, revealing a cosmic rhythm of staggering length. This geometric view of the heavens reached its most radical conclusion with Aristarchus of Samos. He proposed a model that was centuries ahead of its time, a universe with the sun, not the Earth, at its center. Using brilliant geometric reasoning, he even attempted to calculate the relative distances of the sun and moon from Earth. Though his measurements were not perfectly accurate, the method itself was revolutionary. He used the geometry of a triangle during a half-moon to deduce that the sun was vastly larger and farther away than anyone had imagined. His heliocentric idea was ultimately rejected by his contemporaries, but it stands as a testament to the power of pure thought. These Greek astronomers were not merely stargazers, they were architects of cosmic models. They used spheres, circles, and epicycles to simulate the perplexing loops of the planets, translating the messy reality of the sky into a clean, predictable system. Their work demonstrated that the universe was not a chaotic realm of divine whims, but a cosmos, a word they gave us that means an ordered and beautiful system. This shift from recording patterns to modeling underlying principles was a monumental leap. It proved that with logic and geometry, humanity could begin to predict not just when events would happen, but why they occurred at all. Their legacy was a framework of inquiry that would inspire astronomers for the next 2,000 years, a shining example of how a bold new perspective can illuminate the deepest workings of the physical world. While Greek thinkers mapped the cosmos with geometry, a parallel revolution in celestial calculation was unfolding under the Indian sun. There, astronomers perfected a different kind of precision, one rooted in the steady backdrop of the fixed stars and the complex rhythms of the moon. Their foundational text, the Surya Siddhanta, meaning the knowledge of the sun, presented the universe not as a set of physical spheres, but as a system of mathematical relationships. It contained intricate algorithms for predicting planetary positions and eclipses, calculations that required a deep understanding of trigonometry and algebra. At the heart of their system was sidereal tracking, a method that measured the moon and planets against the seemingly permanent tapestry of distant stars. This provided a stable reference frame, a cosmic grid against which even the slightest movement could be detected and logged with extraordinary care. One brilliant mind, Aryabhatta, captured this spirit of inquiry in the 5th century. In his seminal work, the Aryabhatiya, he calculated the length of the solar year to an accuracy of minutes, and he proposed that the Earth was a spinning sphere, explaining the apparent motion of the heavens as a rotation rather than the stars physically circling above us. He even arrived at a figure for the Earth's circumference that was strikingly close to the modern value, all through mathematical reasoning and careful observation. How did they achieve such feats without advanced instruments? Their secret was a unique fusion of spiritual cosmology and empirical rigor. The cosmos was seen as an ordered, cyclical expression of divine principles, and understanding its mathematical order was a path to deeper truth. This philosophical drive fueled the creation of incredibly precise lunar calendars. They didn't just track the moon's phases, they calculated its subtle wobbles and varying speed, creating a lunisolar calendar that reconciled the lunar month with the solar year through the intelligent addition of extra months. This ensured that festivals tied to the moon cycle still occurred in their proper seasons, a practical need that demanded and rewarded astronomical excellence. Their legacy is a powerful reminder that the quest to predict cosmic cycles took many forms, from the geometric models of Greece to the profound computational astronomy of India, each culture finding its own path to mapping the eternal rhythms of the sky. Meanwhile, in the courts of Imperial China, the night sky was a state archive. For over 2,000 years, court astronomers kept a continuous, meticulous watch, logging every anomaly with bureaucratic precision. Their records note the sudden appearance of guest stars, what we now call nova, and carefully charted the paths of sweeping comets through the constellations. This was not merely science, it was a matter of national security. The fundamental belief was the mandate of heaven, the philosophical principle that the emperor's right to rule was granted by the cosmic order itself. An unexpected event in the heavens, like a brilliant comet or an eclipse, could be interpreted as a sign that the mandate was in question, that the emperor had lost the favor of the cosmos. This created an immense, unbroken incentive for accuracy. A mistake in observation or prediction was not just an error, it was a political crisis. This system ensured that astronomy was a state-funded, rigorously maintained institution for centuries. The same imperial bureaucracy that collected taxes and maintained the army also employed astronomers to watch the sky every single night. This long-term commitment yielded an astonishing discovery. By comparing records across dynasties, Chinese scholars realized that one particular comet returned to the inner solar system again and again. We know it today as Halley's Comet. Their archives contain clear descriptions of its appearances stretching back to at least 240 BC, a continuous log of its visits that modern astronomers still rely upon. This fusion of celestial divination and administrative diligence created something priceless, a multi-millennial dataset. It was the ultimate validation of their methods, proving that what began as a search for heavenly omens could, over generations, reveal the deep, predictable rhythms of the cosmos itself. Massive stones still stand as silent witnesses to an ancient understanding of the sky. From the windswept Salisbury Plain in England to the arid mesas of the American Southwest, our ancestors engineered the landscape itself into a cosmic clock. Stonehenge, with its iconic ring of towering Sarsens, is perhaps the most famous example. On the summer solstice, the rising sun aligns perfectly with the heel stone, casting a beam of light deep into the heart of the monument. This was no accident. It was the result of meticulous planning and generational effort, a permanent marker for the sun's northernmost reach. Far across the Atlantic, at Choco Canyon in New Mexico, a different kind of calendar was carved into a high cliff face. A spiral petroglyph serves as a precise solar target. At noon on the summer solstice, a slender dagger of sunlight slices directly through the center of the spiral. As the days pass, the dagger moves, tracing the sun's journey toward winter. These structures were not passive temples, they were active, functioning instruments. They translated the abstract movement of celestial bodies into a tangible, visual event that anyone in the community could witness. The engineering required was immense. Transporting multi-ton stones over vast distances or carving perfect light shafts into rock faces demanded a sophisticated knowledge of mechanics and geometry, all in service of capturing a cosmic rhythm. This reveals a profound truth. Their astronomical knowledge was not confined to a few elite scribes. It was built into the very world people lived in, a shared public science etched in stone and light. The solstice alignment was more than a calendar date. It was a communal experience that reaffirmed their connection to the cosmic order, telling them when to plant, when to harvest, and when to gather for ceremony. These megalithic observatories are a powerful testament to a universal human impulse to harmonize our lives with the grand, predictable cycles of the universe, using the most durable materials at our disposal to make the eternal cycles of time visible for all to see. These celestial discoveries were never truly lost in the silence of history. They traveled, carried along the bustling trade routes that connected the ancient world. A Greek astronomical text might be translated in the Great Library of Alexandria, then studied by a scholar in Baghdad centuries later, who would add his own brilliant commentary before the work eventually found its way to a monastery in medieval Europe. This was not a linear path but a vast, interconnected web of knowledge. When Islamic scholars encountered the works of Greek thinkers like Ptolemy, they did not merely preserve them. They questioned them, tested their calculations against the clear desert skies, and built upon them with groundbreaking new instruments and mathematical techniques. The astrolabe was perfected in these workshops, becoming a masterpiece of metal and mathematics. These enhanced ideas, now carrying the imprint of multiple cultures, eventually crossed into Europe, where they ignited the scientific revolution of the Renaissance. A similar exchange unfolded with the sophisticated mathematics developed in India. The concept of zero and advanced trigonometric methods journeyed westward into the Arab world, where they were embraced and refined, eventually providing European astronomers with the computational tools they needed to challenge the old models of the cosmos. This constant, cross-cultural flow of ideas meant that no civilization had to start from scratch. A Mayan priest observing Venus and a Chinese court astronomer tracking a comet were part of the same grand human project, even if they never knew of each other's existence. Their collective effort reveals a profound truth about our quest to understand the universe. Science has never been a solitary endeavor. It is a collaborative inheritance, a conversation across centuries and continents, where each generation stands on the shoulders of all those who looked up and wondered before them. The planets presented a stubborn puzzle, moving at varying speeds and occasionally doubling back in bewildering loops. To tame this celestial chaos, ancient astronomers devised an elegant mathematical solution, breaking complex motions into simpler, repeating parts. They identified periods, the fixed intervals after which a planet would return to the same position against the stars. This was the fundamental rhythm, the steady beat underlying the apparent dance. But the looping retrograde motion demanded a more creative fix. The answer was the epicycle, a brilliant conceptual tool. Imagine a planet moving in a small circle, whose center itself travels along a larger circular path around the Earth. When the planet on its little circle moves backward relative to the larger path, we on Earth see it perform its temporary reverse loop in the sky. This model of circles upon circles, while not physically correct, was a stroke of mathematical genius. It provided a predictive framework that could be fine-tuned with painstaking observation, reconciling the elegant theory of uniform circular motion with the messy reality of the wandering stars. The ultimate expression of this geometric thinking was a marvel recovered from an ancient shipwreck, the Antikythera mechanism. This intricate bronze device was a portable cosmos powered by hand. Through a complex system of precisely cut gears, it modeled the epicyclic motions of the planets, predicted eclipses, and even tracked the schedule of the Olympic Games. Turning its handle was like winding forward the cosmic clock, watching a miniature universe obey the mathematical rules its creators had deduced. This was not mere philosophy, it was a working simulation of the heavens. Their achievement proves a profound point about the human mind. You do not need calculus to grasp the mathematics of the cosmos. With patient observation and a clever application of geometry, they built a bridge between the perfect world of numbers and the dynamic reality of the night sky, creating a predictive power that would stand for centuries. The open ocean presented an immense trackless challenge, a realm where landmarks vanished and the horizon stretched into infinity, yet ancient mariners did not sail blind. They possessed a map written not on parchment but in the stars themselves. For Polynesian voyagers, the Pacific was not an empty void but a familiar highway, its routes charted by a deep, generational knowledge of the night sky. They memorized the precise rising and setting points of key stars, using them as celestial compass points. A star known to ascend directly over a distant island chain became a reliable beacon, its path across the heavens a guiding line etched in light. But their mastery went beyond the stars alone. They learned to read the subtle patterns of ocean swells, feeling how they reflected off unseen islands, and they watched for specific species of birds that never ventured far from land. This was a holistic science of wayfinding, a fusion of astronomy, meteorology, and biology that allowed them to colonize the most remote islands on Earth. Across the world in the Mediterranean, sailors look to a different, unwavering guide, the North Star, because it holds a nearly fixed position above the Earth's North Pole. Its altitude in the sky provided a constant measure of latitude. The higher it appeared, the farther north a ship had traveled. This single point of light transformed exploration from a dangerous gamble into a calculated endeavor. It enabled the Phoenicians to establish trade routes across the entire Mediterranean and venture out into the Atlantic, carrying goods and ideas between continents. This practical application of astronomy fundamentally reshaped the human world. Predictable star positions and seasonal wind patterns, meticulously documented by generations of sky watchers, were the invisible infrastructure for global trade and cultural exchange. Spices, silks, philosophies, and technologies could now journey across thousands of miles of open water. The ability to predict the cosmos was not an abstract intellectual exercise, it was the key that unlocked the planet. Every long-distance voyage, every connection between distant cultures, was underwritten by this ancient celestial wisdom. The legacy of these navigators demonstrates a profound truth, that by learning to chart the heavens, humanity finally learned to chart its own place on Earth. The line between reading the stars and reading a divine message was often invisible. In the ancient world, the astronomer and the astrologer were frequently the same person, their work supported by a single, powerful belief that the cosmos and human destiny were woven together. This was not seen as superstition, but as a sophisticated science of interpretation. Babylonian scholars meticulously tracked the path of Jupiter not merely to log its position, but to forecast the economic health of the kingdom or the success of the harvest. The Greek-Egyptian scholar Claudius Ptolemy, who gave us a masterful geometric model of the universe in his Almagest, also authored the Tetrabiblos, a foundational astrological text that linked planetary alignments at a person's birth to their character and fate. For these thinkers, observing a planet's motion and interpreting its meaning were two sides of the same coin. This deep connection provided something crucial, a compelling societal justification for the immense labor of astronomy. Kings and emperors funded observatories and sponsored scribes not for abstract knowledge, but for vital intelligence. The ability to predict an eclipse or a planetary conjunction was directly tied to matters of state security, royal legitimacy, and public morale. A court astrologer's warning, based on a rare celestial event, could influence the decision to go to war or delay a coronation. This practical demand created a self-perpetuating cycle. The need for accurate astrological interpretation drove the need for ever more precise astronomical data, which in turn refined the predictions, justifying further observation. While modern science has carefully separated the two disciplines, this historical bond was the engine that powered centuries of discovery. To dismiss it is to miss the very human motivation behind the numbers. Their quest was not just to map the heavens, but to find meaning in its movements, a desire to see our own stories reflected in the vast, orderly expanse above. The fragile clay tablet, once fired in a kiln, could outlast empires. Across continents and centuries, the survival of celestial knowledge hinged on this stubborn physicality, on the labor of countless hands dedicated to preservation. In Mesopotamia, the cuneiform astronomical diaries were not just stored, they were systematically archived in great libraries, creating a permanent data bank for the future. When the Great Library of Alexandria gathered scrolls from across the known world, its scholars were engaging in the same essential act, compiling the observations of Babylonians, Greeks, and Egyptians into a single, grand repository of human understanding. But libraries are vulnerable to fire and conquest. The true lifeline for this knowledge proved to be the unbroken, quiet work of scribes. In secluded European monasteries, through the so-called Dark Ages, monks meticulously copied not only religious texts but also ancient astronomical and mathematical works, their quills tracing the geometric proofs of Euclid and the planetary models of Ptolemy onto fresh vellum. This was not merely transcription, it was an act of faith in knowledge itself, a belief that these ideas were too precious to be lost to time. Simultaneously, in the vibrant intellectual centers of the Islamic world, a parallel and equally vital effort was underway. In cities like Baghdad and Damascus, scholars translated thousands of ancient texts into Arabic, adding their own meticulous commentaries and corrections. They did not simply preserve, they refined, testing old star charts against the night sky, and developing new mathematical techniques that pushed the science forward. This global, multicultural relay race ensured that when European scholars began to reawaken to classical learning, the works of the ancients were waiting for them, having been safeguarded through centuries. The survival of a single calculation, from a Babylonian clay tablet to a Greek scroll, to an Arabic manuscript, and finally to a printed book in Renaissance Europe, represents one of humanity's greatest, quietest triumphs. It underscores a profound truth that the advancement of science depends as much on the patient curators of knowledge as it does on the brilliant discoverers. Without these dedicated individuals and the cultural institutions that supported them, the chain of insight stretching back thousands of years would have been broken, and each new generation would have been forced to start from scratch, forever losing the hard-won precision of their ancestors. Even with their profound insights, the ancient sky watchers navigated a cosmos filled with obstacles. Their naked eyes were the only lenses they possessed, forcing them to rely on the clarity of the night air, which was often anything but clear. A thin veil of high cloud, a night of excessive humidity, or the simple flicker of starlight in the turbulent atmosphere could introduce tiny errors into their most careful measurements. These minute discrepancies, almost invisible over a single lifetime, could accumulate across generations, slowly pulling their celestial forecasts out of alignment with the actual sky. The most stubborn challenge lay in the perplexing dance of the planets. While their models of epicycles and geometric spheres were brilliant mathematical workarounds, they were ultimately approximations of a deeper reality they could not yet see. A prediction might hold for decades, but eventually, the observed position of Mars or Jupiter would begin to drift from its calculated path, a silent testament to the imperfections in their cosmic clockwork. This required a continuous process of refinement, a new generation of astronomers inheriting the records of their forebears would have to reconcile the accumulating data, sometimes adjusting the established cycles or fine-tuning the parameters of their models. These corrections were not seen as failures, but as a necessary part of the scientific craft. The great Greek astronomer Ptolemy himself revised earlier Babylonian eclipse cycles, not discarding them, but building upon their foundation to achieve a better fit with the latest observations. This iterative process of prediction, observation, and adjustment reveals the true nature of their endeavor. It was a living science, a conversation with the cosmos that was always ongoing. Their legacy is not one of infallible perfection, but of a resilient and adaptable methodology. They demonstrated that the path to understanding the universe is not a straight line, but a spiral of ever-deepening insight, where each small correction brings us closer to the underlying truth. The fundamental principles that guided ancient astronomers still form the bedrock of our cosmic understanding today. Our modern tools are exponentially more powerful, yet the scientific process itself remains a conversation between observation and prediction. A space telescope captures light from a distant galaxy, and a supercomputer simulates its evolution over billions of years. At its core, this is the same intellectual exercise a Babylonian scribe performed when he used centuries of eclipse records to forecast the next one. Both are building a model of reality, testing it against data, and refining it to better mirror the cosmos. The core methodology of watching, recording, and modeling is a timeless thread connecting the clay tablet to the quantum computer. This continuity reveals that technological advancement, while revolutionary, is an extension of an ancient and deeply human way of thinking. We have not replaced their methods, we have accelerated them with tools that expand our senses beyond the limits of the naked eye. A satellite orbiting Jupiter is, in a philosophical sense, the direct descendant of a Greek armillary sphere, both designed to measure what the unaided human cannot. Our digital simulations are the ultimate expression of the epicycle model, using vast computational power to solve the same gravitational puzzles that once required circles upon circles. What does this enduring legacy tell us? The true engine of discovery is not the tool in your hand, but the relentless curiosity in your mind. The journey from tracking shadows on the ground to mapping the cosmic microwave background is not a story of replacement, but of evolution. By studying the ingenious techniques of the past, we gain a profound appreciation for the intellectual bridges that span the centuries, reminding us that every modern discovery stands upon a foundation laid by patient observers who first learned to read the sky. This newfound power to forecast the heavens did more than just mark the seasons. It sparked a revolution in human thought. If the cosmos operated with such unwavering regularity, what did that say about our own lives? Were human actions and destinies similarly bound by an unchangeable script written in the stars? This question of fate versus free will become a central puzzle for the era's greatest minds. The Stoic philosophers of ancient Greece and Rome saw the predictable cosmos as the ultimate expression of a rational, divine order. For them, to live a good life was to align one's own will with this cosmic harmony, to accept one's place in a grand, predetermined design. This was not a surrender to fate, but a path to inner peace through understanding the universe's logical structure. Far across the world, Mayan thinkers arrived at a different yet equally profound conclusion. Their universe was not a linear march toward an end, but a great spinning wheel of time. History itself was cyclical, with ages of creation and dissolution repeating in vast, predictable patterns. Within this framework, human agency was not erased but contextualized. The goal was not to break free from the cycle, but to navigate its turns wisely, to perform the correct rituals at the precise celestial moments that would maintain the balance of the world. This philosophical depth did not distract from their science, it fueled it. The drive to understand whether the universe was deterministic or open to influence encouraged ever more precise observations. A scholar tracking a planet's path was not just collecting data, he was probing the very nature of reality itself. Was he merely documenting an unchangeable decree, or was he learning the rules of a cosmic game that still allowed for play? These debates transformed astronomy from a mere technical craft into a deeply humanistic pursuit, connecting the measured motion of a planet to our most enduring questions about choice, responsibility, and our small but significant role in a vast, ordered cosmos. Our modern scientific world still runs on codes written by ancient sky watchers. Consider the simple act of looking up a star's position, a task that relies on a coordinate system first mapped onto the celestial sphere by Greek astronomers. We still divide the circle into 360 degrees, a convention refined in Babylon from their base 60 number system, perfectly suited for their astronomical calculations. This is more than a historical footnote. It is the living architecture of our navigation, our mathematics, and our engineering. The legacy extends far beyond the classroom. The entire discipline of climate science depends on the very same methodology those early observers perfected: long-term data collection and pattern recognition. Just as Babylonian priests logged eclipse cycles for centuries, modern scientists analyze ice cores and sediment layers, searching for the deep rhythms of our planet's climate across millennia. Archaeologists use their techniques in reverse, applying knowledge of ancient star alignments to date forgotten structures and understand the celestial beliefs of past cultures. The most stunning validation of their sophistication emerged from the depths of the sea. The Antikythera mechanism, a corroded lump of bronze recovered from a shipwreck, was eventually revealed through advanced imaging to be an intricate analog computer. Its complex gearing precisely modeled the motions of the sun, moon, and planets, predicting eclipses and tracking the cycles of athletic games. This single device shatters the notion of ancient technology as primitive. It proves that the conceptual leap from observing patterns to building a physical simulation of the cosmos had already been achieved over 2,000 years ago. Their work was not a prelude to real science, it was the foundation upon which all later discovery was built. The next time you check a satellite forecast or see an image from a space telescope, remember the long chain of observers whose patient gaze first taught us how to measure the universe. Some stories suggest ancient sky watchers received their knowledge from otherworldly visitors or a forgotten advanced race. Yet the truth, pieced together from clay tablets and stone inscriptions, reveals a far more compelling narrative of human achievement. The Great Pyramid of Giza, for instance, is often cited for its near-perfect cardinal alignment. This was not the work of alien technology, but of simple, brilliant surveying. By tracking the circular path of a star around the celestial pole, Egyptian engineers could establish a true north-south line with nothing more than a sighting tool and immense patience. This method is documented, repeatable, and entirely within the capabilities of the people of that time. The same principle applies to the so-called mystery of ancient eclipse predictions. We have the Babylonian clay tablets that detail the Saros cycle, and we have the Greek geometrical models that calculated lunar motion. There is no gap in the historical record that requires an outside explanation, only a continuous, traceable line of human problem solving. These myths, though captivating, inadvertently rob these cultures of their rightful credit. To attribute their accomplishments to extraterrestrials is to dismiss the generations of disciplined observation, the slow refinement of mathematical techniques, and the powerful cultural motivations that drove them to such precision. The real wonder is not that someone else gave them this knowledge, but that they discovered it for themselves through perseverance and intellectual courage. Their legacy is a testament to what human curiosity can accomplish when it is sustained across centuries, a powerful reminder that our ancestors were not primitive but profoundly ingenious. The story of ancient astronomy is often told through the names of great men, but the full picture reveals a far richer collaboration. Women were also vital observers and interpreters of the cosmos, their contributions woven quietly into the fabric of celestial knowledge. In ancient Sumer, the high priestess Enheduanna, who lived over 4,000 years ago, composed hymns that wove together the movements of the moon and the planet Venus with the power of the gods. She was not merely a poet, she was a celestial chronicler, her words helping to establish a cultural framework where the sky was central to spiritual and political life. Centuries later in Alexandria, Hypatia stands as a monumental figure, a philosopher and mathematician who taught the intricate geometry of the heavens and crafted advanced astronomical instruments. Her tragic passing marks a profound loss, yet her legacy endures as a powerful reminder of the intellectual heights women could achieve, even in societies that often limited their public roles. Beyond these well-known names, countless women participated in this work from within their own cultural contexts. In ancient China, female oracle bone interpreters held a sacred responsibility. They were part of the process of reading cracks in heated bones, a practice that often sought divine guidance based on celestial events like eclipses or comet sightings. Their interpretations of these sky-born omens could influence the decisions of emperors, making them indirect but crucial participants in the state-sponsored science of the heavens. These diverse voices, from priestesses to scholars, demonstrate that astronomical knowledge was not cultivated in isolation. It was a collaborative human endeavor that crossed genders and social roles, a tapestry woven from many different threads of insight and experience. To overlook their part in this story is to miss the true, collective nature of our ancient quest to understand the universe. Their long-term perspective offers a vital lesson for our own era. We face challenges that unfold over centuries, like the slow shifts in our global climate or the immense timelines required for interstellar travel. These are not problems that can be solved within a single election cycle or a single human lifetime. The ancient astronomers understood this kind of thinking instinctively. Their work was a relay race where one generation passed the baton of celestial data to the next, trusting that their great-grandchildren would see the pattern they had only just begun to trace. This multi-generational commitment to pure data collection without any guarantee of immediate reward is perhaps their greatest gift to modern science. Imagine if we applied the same patient diligence to our own planetary observations. What if we committed to measuring ocean temperatures or atmospheric compositions with the same unwavering consistency that Babylonian scribes logged the movements of Jupiter? The result would be a data legacy of unparalleled power, a definitive record of planetary change that could guide humanity for 1,000 years. Their methods also teach us the profound value of interdisciplinary thinking. The Mayan astronomer was also a priest and a mathematician. The Greek cosmologist was often a philosopher and an engineer. They did not compartmentalize knowledge. In our specialized world, tackling a challenge like climate change demands a similar fusion of insights from physics, economics, sociology, and ethics, all working in concert. This ancient model encourages us to lift our gaze from quarterly reports and annual goals to think in what we might call cosmic time scales. What scientific questions are we asking today that only our descendants will be able to answer? What data are we collecting now that will be priceless to generations 7 centuries from now? By embracing their far-sighted vision, we can transform our scientific endeavors from short-term projects into a lasting conversation with the future, building a bridge of knowledge as sturdy and enduring as the stone circles they left behind. You can step outside tonight and use the very same observational methods perfected thousands of years ago. Begin with the moon, our most constant celestial companion. Instead of just glancing up, track its phases on a simple paper calendar for a full cycle. Mark the day it is a thin crescent when it is full and when it vanishes into the new moon. This simple act of logging transforms casual viewing into a disciplined practice, mirroring the first steps of every ancient astronomer who ever sought a pattern in the sky. Next, choose a single bright star. Go out at the same time each week and note its position relative to a fixed landmark, like a rooftop or a distant tree. You will soon see it drifting steadily westward, a slow march that reveals the Earth's own journey around the Sun. This is sidereal tracking, the same technique used by Indian astronomers to build their star-based cosmic grid. For a truly hands-on experience, plant a straight stick firmly in the ground to create your own gnomon. Throughout the day, mark the tip of its shadow with small stones. You will trace a graceful arc, and the shortest shadow you record will point directly to local solar noon, revealing the sun's highest point in the sky for that day. Repeat this around the solstices, and you will personally measure the sun's changing path, just as they did at Stonehenge and Choco Canyon. These activities require no special equipment, only your attention. They force you to slow down and truly see the sky's gradual dance, building a foundational skill that no app can provide. By engaging in this ancient rhythm of watchfulness, you do more than just learn about the stars. You become part of an unbroken human tradition, connecting your own curiosity directly to the patient, wonder-filled gaze of the very first sky watchers. The story of how ancient astronomers predicted cosmic cycles is a testament to human creativity, patience, and intellectual courage. From the Babylonian clay tablets to the Mayan codices, their achievements remind us that the quest to understand the universe is a fundamental part of our heritage. Their methods, rooted in careful observation, mathematical innovation, and cultural dedication, laid the groundwork for the scientific revolutions that followed.